A 2 kilogram object is initially at rest on a smooth horizontal surface. Initially at rest meaning that the velocity is 0 at time t equals 0, and smooth meaning that there's no friction. The mass is then acted on by this force of magnitude 10 newtons and this one of magnitude 5, and they cause the mass to move horizontally. So therefore we can assume that the force in the y direction is 0. The aggregate force, the total force in the y direction. The task, or part A at least, is to find the normal reaction force, so let's go ahead and do that. So what I recommend doing to get this problem started is actually to draw your own diagram. And the reason is this. If you look at this diagram you're given, we are given these force vectors, which is great, but unfortunately they're labeled with just their magnitudes. So we're not actually given the breakdown of the vector into its components. And that's kind of a pain in the ass for us because we're trying to find the normal reaction force, which is a force in the y direction. So obviously breaking up into x and y's is very useful. So what we're going to do is we're going to draw our own diagram. There's this force. This 10 newtons force is going to become 10 cos 60 degrees sine 60 degrees. That's just coming from here. If you're a bit unsure about where that comes from, it's this. So if we have a right angled triangle and the hypotenuse is r and this inscribed angle in here is theta, the adjacent length is always going to be r cos theta and the opposite length is always going to be r sine theta. So if you've never seen that before, it's good to memorize this triangle. Super helpful in regards to all things vectors. So I'll go ahead and draw the other force vector on. We have 5 cos 30 degrees, comma sine 30 degrees. And I'm also going to put a negative here. And the reason for this negative is basically that if you look at this triangle, you'll notice that the x contribution is actually in the negative x direction. So therefore, to accommodate that, we need to put a negative out here. I'll now go ahead and draw a vector for the force of gravity. And obviously this isn't moving us left or right, so I'm going to put 0 for the x component. And I'm going to put negative 2g for the y component. The reason is the strength of gravity is mg, or the force due to gravity is mg. And we know the mass is 2, so that's 2g. And we also know it's pointing down, so therefore we get negative 2g. Finally, I'll go ahead and draw a normal reaction force here. Once again, it's not moving us left or right, so we'll put 0 in the x component. And we'll write capital N for the strength of that normal reaction force. So now the task is to find the normal reaction force, so we're trying to find an expression for N. And you can see that N is in a y position. It's a y component. So therefore what we want to do is we want to add up all the y components we see in front of us, and hopefully that's going to tell us what capital N is. So I'm going to start on the left here. 5 sine 30 degrees plus n. And now we'll add up this contribution. So that's 10, let's put in the degree symbol, 10 sine 60 degrees minus 2g for this y component. And we know that equals 0. And the reason is, remember, the forces cause the mass to move horizontally. And therefore the sum of the forces in the y direction, they have to be 0. So at this point, we can go ahead and rearrange. So I want to get n by itself. Everything else goes to the other side of the equal sign, so the signs flip. The negative 2g becomes positive 2g. We get minus 5 sine 30 degrees here, minus 10 sine 60 degrees here. And then we just need to put in the values of these trigonometric expressions. So sine 30 degrees is a half, sine 60 degrees is root 3 over 2. Personally, when I was going through the education system, I found it quite hard to remember how these values all worked. So I'll give you a little trick for remembering them. So personally, I could always remember these key angles, 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And I was always able to remember these key trigonometric values. So 0, half, root 2 over 2, root 3 over 2, and 1. But the bit that would always trip me up was just pairing them off. So in particular, is sine 30 degrees half, or is sine 30 degrees root 3 over 2? This would always trip me up, personally. So here's what I recommend for remembering this. Let's get rid of the angles, because they're easy to remember in our head. or let's say it like this, they're easy to keep in our head. And what we'll do is we'll put sine on the left here, and we'll put cos on the right-hand side here. And the idea is this. For sine, we start counting from the left. So sine 0 degrees is 0. Sine 30 degrees is a half. That's that number. Sine 45 degrees is root 2 over 2. Sine 60 degrees is root 3 over 2. That's that number. And sine 90 degrees is 1. And for cos, it's exactly the same, but we start counting from the right. So I find that if you just keep this diagram here, I've actually lost a left-facing arrow. If you keep this diagram here in your mind, it's going to be very easy to work out what these values are. And if you can't keep it in your mind, just jotting this down on a little bit of paper at the beginning of your exam will allow you to work out those values very easy and very reliably. Okay, so let's go ahead and simplify. 5 times a half doesn't really simplify, it's just 5 over 2. 10 over 2 does simplify, it's 5. And we'll put a root 3 here. You don't need to go any further than this. You don't have to put 9.8 in for g, for example. The convention in specialist math is that if you're not told what form to give the answer in, just give it an exact form, but they want an exact form answer unless they tell you otherwise. And so because of that, we don't need to put 9.8 in for g. This is a complete answer as is. So the normal reaction force equals 2g minus 5 over 2 minus 5 root 3. Now, you're not going to lose marks if you don't put in the units, but I'm going to put them in. And the reason is this. If you get into the habit of not putting in your units, you might not get burnt in this particular exam, but there will come a time when you start losing marks for no reason, because you're going to be in a subject where they actually care about that. So therefore, I just find that it's better to be in the habit of reporting your units on the final line, and that way you'll never accidentally lose marks because you left them off. And this is very relevant also if you're doing physics as well as specialist math. They do care about the units in physics, and so I strongly recommend just getting into the habit of just always putting your units in. For task B, we need to find the acceleration of the mass in meters per second after it begins to move. So to do that, what we're going to do is we're going to focus in on the force in the x direction. This is pretty easy. So this x component is 0. The normal reaction force also doesn't have an x component. So there's only two things we need to include. We need to include the negative cos 30 degrees here and the cos 60 degrees here. So I'll do that now. And once again, you should be able to work out these trigonometric values from that table we just saw. Cos 30 degrees is quite large because we're counting from the right. And cos 60 degrees is quite small because by the time we've moved all the way, most of the way towards the left, we're at a half. If you can't see that just off the top of your head, or if you can't visualize it, just go ahead and draw that table and rely on the table. Don't take risks with the marks because you really want to get every last mark you can on these crazy exams. All right, let's clean up our working, or clean up our numbers. I'm going to go ahead and pull out 5 over 2 just to make it a bit nicer. So we're going to get a negative root 3 here, and we'll get a plus 2 here. The reason for the plus 2, this 5 goes down to 1 because we took out a 5 here, but we need to double that. We need to double that 1 because we have a 2 in the denominator. Now, we're not quite done. We're trying to find the acceleration. This is just the force. We found the force. So remember, the acceleration is always going to be the force divided by the mass. And in this case, the mass is 2, so therefore we know the acceleration is going to be 5 over 4, 2 minus root 3. Let's write that in with our units. I'm going to write A equals 5 over 4, 2 minus root 3 meters per second. Now you'll notice I've left off the subscript x here, and that's because we know the acceleration is entirely in the x direction. So therefore the magnitude of the acceleration will actually be the size of the x component. There is a little subtlety here, which is that we need to check technically that this is positive, and we haven't done that. Now, it's quite obvious to me that it's positive, but if it's not obvious to you, I want to give you a technique that's going to help you check whether or not a number is positive. So here's how the technique works. We start off by writing TFAE. This stands for the following are equivalent. Super useful. This is all over my working out. So the following are equivalent, and then we're going to conjecture that the number of interest, so A, is positive. And then we're just going to check that it really is. So we start off by putting in our number. Okay, this first line is obviously equivalent to the second line, which is equivalent to this. I'm going to move the root 3 over. Then we can square. And this is clearly true. And each line here in this list is equivalent to the previous line. So therefore, we learn that true is equivalent to A greater than 0. So therefore, our value for A is positive, and therefore our answer is correct. Okay, so for part C, we're trying to find out how far the mass travels in meters during the first 4 seconds of motion. So I just put a big 4 there for us to help us out a bit later. Now, to solve this, I think it's best to think of the constraints of the problem as a differential equation. So let's say the second derivative of x, so that the x position with respect to time, is going to be the acceleration in the x direction. And this is constant, so therefore we can solve this. So the position at time t should be the initial position plus the initial velocity times the time taken plus the initial acceleration. So we could write x double dash of 0 here, but I'm just going to write ax because we know it's constant, times t squared over 2. And we actually know a lot of these numbers, right? So we can think of the initial position as 0. So this is going to vanish in the next line. The initial velocity is given as 0. Remember, it's initially at rest. So we can assume x dash of 0 is 0. And therefore, our solution is going to simplify. So x at any time t, so the position at any time t, should be this constant acceleration times t squared over 2. Now, the other bit of information we've got is this number 4. So we're interested in the time t equals 4 because it's the first 4 seconds of motion that we're interested in. So I'm going to write, for the next line, the position at time t equals 4 equals ax times, now t squared will be 4 squared, which is 16. Divide by 2, we get 8. So I'm going to write times 8. And we already know ax. I've written it as a here, but ax and a are the same thing in this context. We know this is 5 over 4 times something, and we're trying to multiply by 8, so this over 4 will cancel with the times 8, and we'll end up with a times 2 in our next line. So 2 times 5 is 10. I'll put a 10 out here, and there's our answer, okay? So the distance the mass travels in the first 4 seconds is x of 4 equals 10 times 2 minus root 3 meters.